Bismillahirrahmanirrahim. Assalamualaikum and hi. My name is Aiman Rosli. First of all, I would like to thank to my beloved supervisor, Dr. Muhammad Razli bin Ahmad, and also my beloved internal examiner, Dr. Chap Savuti, and my external examiner, Encik Muhammad Azmin Ishaq. My title for final year project is Harvesting Ambient RF Energy for Charging Low Power Devices. Ladies and gentlemen, hereby I will explain about the problem statement regarding this project. So the conventional wire charging system limits the movement of device user, and the users are required to find source of electricity in order to recharge the devices. This is the problem statement that we found, and this project can overcome this problem. So the objectives of this project is to study on the feasibility of wireless charging using RF energy, harvesting for charging low power devices. And the second objective is to improvise charging system of harvesting ambient RF energy to electrical energy. And then the third objective is to boost up the power input in order to supply the sufficient amount of power. In order to understand deeper about this project, some research has been done. So the first literature review is on the energy harvesting. There are a few types of energy harvestings, such as piezoelectric harvesting, thermoelectric harvesting, microwave harvesting, wind energy, solar energy. So the difference is that they are harvesting on different type of source, such as the piezoelectric harvestings, the material captured pressure is from low frequency vibration. But for thermoelectric harvesting, the source of the energy is through temperature. And then I also studied on the RF energy harvesting system and found out that the standard component RF system consists of a receiver antenna, matching circuit, and rectifier. And then the third is the antenna. Antenna is a transducer that converts RF signals into AC. There are a few types of antennas, such as broadband antenna, dual polarized patch antenna, microstrip patch antenna, and coplanar waveguide antenna. So each of the antenna has each specific power in and power out based on the type and also based on the waveform captured. Example, on the broadband antenna, the power in is minus 40 dBm to minus 20 dBm. Next, we proceed with methodology. First methodology is by having a project planning. I did some research on the various topics related to this harvesting ambient RF energy for charging of low power devices. And my focus area of this project is in indoor environment, since we find out that each of the indoor place, such as office, home, there will be a Wi-Fi router and also a Wi-Fi signal. Therefore, in this project, I focusedly on the Wi-Fi signal. And then I will be doing some project analysis on the strength of power signal from the Wi-Fi. So I analyze the RF energy harvesting system. How I analyze is by downloading the mobile applications for checking the strength of power signals. And then this is the result that I gain. This is the distance of my mobile application connected to the same SSID Wi-Fi, and also the distance is from my mobile with the router. So if 1 meter, the signal strength is minus 30 dBm. 10 meter distance is the minus 62 dBm, and 50 meter is minus 73 dBm. Next method is on designing and simulating the project. And then the first one is the antenna. The microstrip antenna model is chosen. And the operation frequency will be only sickle band, which is 2.4 GHz. Here is the top view of the antenna. And second, on the matching impedance circuit, the R in is designed with a value of 50 ohm, and the expected load resistance is 100 mega ohm, and the frequency is still the same, is 2.4 GHz. So the circuit of the matching impedance I use here is the low pass downward time match. Here is the simulating circuit, schematic circuit. And then the third is on designing on the rectifier. The type of the rectifier I choose is the full wave bridge rectifier, and here is the schematic design on the simulation. Next, we proceed with the result and discussion. First result is on the simulation output, and then the first specification is on the antenna. Based on the simulation, I'm using the CSC software. in order to achieve the impedance value of 50.79 ohm, so the value for H and W is 1.5 millimeter and the W is 2.98 millimeter. And then in order to increase the effectiveness on capturing the Wi-Fi signal on the 2.4 GHz, the deeper the S11 is, the better. So from this S11, I'm choosing on the 30 run ID, which have the antenna X value is 39 millimeter, antenna Y value is 30.2 millimeter, and intrinsic Y is 5.6 millimeter, and then the bandwidth frequency of the antenna is 2.4 GHz. And then the gain achieved based on the design for the same simulation is 7.042 dBi. So through calculation, the expected voltage will be 0.470 voltage by assuming the resistance is 50 ohm. And then for matching impedance, with using the same schematic circuit simulating, the input voltage I put is a 200 millivolt, and then the output voltage I observe is 100 millivolt. There is some losses after passing through the matching impedance circuit. And then the third simulation is on the rectifier circuit. Before the voltage is rectified, the waveform is captured in sinusoidal, which is in a AC. And then after it's rectified, the voltage captured is a flat line, which is also known as DC. Ladies and gentlemen, hereby is the microstrip antenna design. I'm using the Eagle software to design this PCB design, and this is the PCB actual after the fabrication process. And then hereby is the full bridge rectifier design. This is the schematic design from the Eagle software, and this is the PCB actual. Next, I will explain on the microstrip antenna output result. This result is by using the oscilloscope and checking the voltage directly from the antenna. Therefore, because my design is on single pole antenna, so by having two microstrip antenna, one is for positive, one is for negative, so the maximum output voltage is 132 millivolt and the minimum output voltage is 116 millivolt. And then I combine it, I connect it in series. So for microstrip antenna output, the maximum output voltage, as you can see here, is 220 millivolt and the minimum output voltage is 196 millivolt. So as you can see also here, the voltage is fluctuate within time. Hereby, for this experiment, I recorded from 0 to 120 seconds. And also I connect series for 6 antenna. So the results shown here is the maximum output voltage is 256 millivolt and the minimum output voltage is 216 millivolt. Next, I connected it with the rectifier circuits. After I connect with the rectifier circuit, the output must be in DC. So the voltage is recorded here is increasing by the duration of 120 seconds. It's from 160 to 372 millivolt. The voltage is stored inside the antenna. The voltage is volt inside the capacitor. So as you can see here is so it is connected to the rectifier circuit. So the voltage is increasing in DC, but it will stop when it reaches to 400. So the maximum I can observe is 406 millivolt in DC. So sometimes it will be increasing, sometimes it will be decreasing due to the fluctuate voltage. And then here is my record result for first run of 1 hour test. As you can see, it will sometimes decrease and sometimes increase. And its average is 400 millivolt, 400 to 405 millivolt. So it will be increasing and decreasing. And also this is also the result I can get from the second run of 1 hour test. Hereby is the overall prototype. Ladies and gentlemen, next is the conclusion and recommendation. So the conclusion I can get from this project is the size and the number of microstrip antenna increase the voltage, and the theoretical voltage for the simulation is 0.470 voltage, but the maximum experimental voltage from the microstrip antenna is 0.250 voltage. So the voltage is fluctuate This is due to the strong signal of the Wi-Fi. There is interference at the atmosphere and loss through the impedance of the antenna. Overall, the objectives are successfully met. The system is improvised by having more than one antenna and meet the specified for portable purpose. The input is boosted up by increasing the number of microstrip antennas on harvesting the power from Wi-Fi. So as for recommendation for the future work, first is the improvement of the complete system by design power management circuit that has boost converter, since the lowest input voltage boost converter that available in the market is 400 millivolt. And then the second one is to increase the size of an antenna with the same Wi-Fi bandwidth, which is 2.4 GHz, and observe the result of the improvement of output voltage. And then third recommendation is by having the current probe, we will get the output current and we observe and compare with the experimental and theoretical results. I think that's all from me. Thank you.